All right, so today we're going to run through two sections at once. So it's going to be kind of a lot here. Choose to write down what you choose to write down for your notes. Definitely put a property in maybe the example or expanded form, I guess, would be optional. But this is important to understand why the properties are. Okay, this should be a review from Algebra 1, so we're going to go through these kind of quickly. So our first property of exponents is if I'm multiplying two things that have the same base, like m to the third and m to the fourth. Okay, in expanded form, m to the third would be m times itself 3 times, and m to the fourth times itself 4 times. So altogether, that would be m times itself 7 times. So as you can tell here, to get to 7 from 3 and 4, we would need to add our exponents. So our property here is a to the m plus n. If you multiply two things with the same base, you can keep that base and add the exponent. Okay, for our second property, here if I'm raising something with a power to another power, so a power to a power, like m squared raised to the third power. Remember, this means whatever's in the parentheses times itself 3 times. And m squared means m times m. So if we fully expanded this out, we end up getting 6 m's all being multiplied together, m to the 6. And so we can tell to get to 6 from 2 to 3, we would need to multiply our exponents 2 times 3, or m to the 6th power. So for power raised to another power, we multiply the exponents, m times n. Okay, for our next property, if we were dividing two things that have the same base, so m to the 5th divided by m to the 3rd, well, that would be 5 m's multiplied in the top and 3 in the bottom. And just like we can reduce regular fractions, if we have common factors between the top and bottom, we can reduce those to 1s, anything divided by itself. So we end up with just m squared. And how do we get to 2 from 5 and 3? Well, subtraction, of course. And this hopefully makes sense from our first property. If you're multiplying things with the same base, you add the exponents. If you are dividing things with the same base, you subtract the exponents in the order of the top minus the bottom. Okay, for our next property, this has to deal with what a negative exponent represents, and this is really important. So let's say we took that same fraction and did the reciprocals. Let's flip it upside down. So now there's only 3 m's on top and 5 m's on bottom. Well, once again, if we cancel out 3 sets of m's by basically reducing them to 1s, we're going to end up with 1 over m squared. So here, if we use the previous property, right, of subtracting the exponents, 3 minus 5 would give me negative 2. We've now gotten a negative exponent. And if we look over here, the correct final result from our expanded form, we can tell what that means when you get a negative exponent is if you make this a fraction, you take the term or whatever has our negative exponent placed on it, and you bring it to the denominator or change its place in the fraction. And then the exponent becomes positive. So to make a negative exponent positive, change its place in the fraction. Here we needed to move m squared to the bottom. So our property over here, if you have a to the negative m, think of this as over 1, you'd move that to the bottom and get a to the positive m in the denominator. Anything to the 0 power, some of you guys might have this memorized, but here's why. Let's say you have m to the 3rd divided by m to the 3rd. Well, from our expanded form, we know these all reduce to 1, so we end up with just 1. So again, if we use the subtraction property that we learned earlier from here, 3 minus 3 would be m to the 0. But of course, we can tell from our expanded form that this has to equal 1. So from this, we can derive that anything to the 0 power is equal to 1. Okay, our next two properties, we're going to do at kind of the same time. If you have just multiplication or division in a set of parentheses, and it's being raised to a power, you can distribute your exponent. So let's take a look at y. So again, if I took this thing and cubed it, it means 5x squared, 5 times x times itself 3 times. Well, here I'm going to get 5 times 5 times 5, 5 cubed, or 125 if we evaluate it. X squared times x squared, which is x squared cubed. So you could think of this as 5 cubed, or 125x to the 6th. So as we look at that, not only did our 5 become cubed, times itself 3 times, but so did our x squared. So this multiplication we were able to distribute over. So that became x squared cubed. And obviously this we would want to simplify further to get to that. So our property here is that you are allowed to take an exponent, and distribute over multiplication. Okay, do not do this if there is addition or subtraction, as we just saw with binomial expansion. Something like this, you cannot distribute your 3 over. Okay, the second property down below, I'm just going to quickly go through this. You can, just like if it's true for division, it's true for multiplication, it's true for division. So we can also distribute our exponent over division. Okay, and you can combine these two properties. If there's just multiplication and division, then the exponent gets distributed kind of to everything. So as we can tell here, if I had this quantity to the third, and we did it times itself 3 times, when you multiply fractions, the top times the top times the top, bottom times the bottom times the bottom, and we can see they both became cubed. And of course this, cubed, this would become x to the third over 125 if we wanted to calculate that out a bit. Okay, I'm just going to run through a few examples here. I know there's 8 on the screen. We probably won't do all 8. Example 1, though, if you're multiplying things that have the same base, this is our very first property back here. Okay, we add the exponents. So this is y to the 12th. Okay, here we've got just multiplication going on, 3 times a raised to the 4th, and we know we can distribute our exponent to both. So 3 to the 4th ends up being 81a to the 4th. Here again, a power raised to a power, this would become m to the 4th. Another power raised to a power, this becomes m to the negative 4th. If I want, now I'm multiplying things with the same base, I can add my exponents, which would give me 0, and that reduces to 1. Another way you could have dealt with this, you could have moved maybe the m to the negative 4 to the bottom and made m to the positive 4th, and then seen that m to the 4th and m to the 4th reduce and also give you 1. So alternate option there. Again, as long as you're using the properties, you'll be okay. Here we have essentially a regular fraction, right? All multiplication in the top and bottom, which means we can simplify a little bit. So dividing top and bottom by 5. In fact, let's do negative 5 to move the negative sign up top. So dividing by 5, and then x to the 4th over x squared. So you can think of this either in expanded form, that there's 4 up top and 2 below. Okay, and then we're canceling out 2 sets, which leaves us with x squared up top. Or if you use the subtraction property, that would be 4 minus 2, which equals 2. Okay, if you use the subtraction property, though, the results you get always starts in the top of the fraction. So if it results in a negative value, you're eventually still going to have to move it to the bottom. All right, so we end up here with really just negative 8x squared. And part of the reason I moved the negative sign to the top is that now I no longer have a fraction at all. So that's pretty nice. Okay, over here I see we've got division and multiplication only, and those are things that we can distribute exponents over. So I get 1 to the 4th. When you raise a power to a power, like 3 to the 4th, you multiply your exponents. Y squared to the 4th becomes y to the 8th. And of course, 1 to the 4th up top is just 1. So we get 1 over x to the 12th, y to the 8th. Here we have all multiplication and division. So let's see what we can simplify. Dividing by 2, we get negative 1/12 for our numbers. We can either subtract these exponents and get c to the 1st, which would be up top, or if you cancel out two sets of c's. That would leave you with one in the top, c to the first. Here again, we can either subtract and get d to the fourth up top, or you can think about canceling the two d's in the bottom with two d's up top, right? Leaving us with 4 in the top. So negative c d to the fourth power, and keep in mind that exponent's only acting on d, not c there, over 12. Okay, this next one, we've got a lot of multiplying. Here I'd like to get rid of these parentheses first, and since it's all multiplication, let's distribute our exponents. We get 2 squared, which would be 4, s squared squared, remember multiply your exponents, and t to the 0 squared would be still t to the 0. In fact, we can get rid of that at any point. Remember, that's going to turn into a 1. Up top, this becomes 16. Let's in fact turn 2 squared into 4. I know this is beginning to be a bit of a mess. So let's see, 16 and 4 dividing by 4 gets me 4 and 1. We've got 6 s's in the top and 4 in the bottom. If I subtract, that's s squared. And then t to the 5th, and this t to the 0 just turned into a 1. So I don't even think we need a fraction anymore. 4s squared t to the 5th. And this last one hopefully is relatively easy. The whole thing is to the 0 power, and anything to the 0 power is 1. So don't waste your time simplifying this if you kind of looked at the big picture there first. Okay, so let's look at some of the ways that we can use our properties of exponents. So these come up a lot in science classes, specifically when we talk about very, very large numbers or very, very small numbers. Right, like distance between planets or the size of a bacteria. So let's practice just remembering how to write things in scientific notation. So remember, in scientific notation, typically we only have at most 3 significant digits, right, or 1 significant digit, I should say, to the left of our decimal place. And then that's usually times 10 to some power, right? So let's practice writing some of these in scientific notation. So if my decimal would normally be here. Let's figure out how to write 2.16 million here. We need to move it to the left 1, 2, 3, 4, 5, 6 places to leave 1 significant digit to the left. And we'd write this as 2.16. All of these zeros become insignificant, as we write them in scientific notation at least, times 10 to the, and how many places do we move it over? 1, 2, 3, 4, 5, 6 times 10 to the 6th power. Okay, and you guys might have known when you have to do this for very, very small numbers, we move this to the left, 1, 2, 3, 4, 5, right, to leave 1 significant digit to the left. So this would be 3.86 times 10 to the negative 5th when we move it to the right for very small numbers. And again, here we're seeing negative exponents. You have seen them before. So not only can we use negative exponents, right, with scientific notation, but check it out, if we need to do calculations with them, like let's say I need to multiply 2 numbers in scientific notation. Rather than expand them out and have to multiply a bunch of excessive zeros, we can actually multiply them in parts. It's kind of like, almost like foiling here, except we're really just going to do 2 parts at a time. It's not really like foiling. Scratch that. So we're going to multiply, the first 2 parts here, 8 times 1.4. Okay, which is 11.2. And then we can multiply these, right? And using our properties of exponents, if we multiply things that have the same base, we can keep the base and add the exponents. So if we add 3 and negative 5, we get negative 2. Now this is almost done, except this is not properly in scientific notation because we have 2 digits to the left. So we need to move our decimal over 1 place to get it in proper scientific notation, 1.12, but that is going to change the exponent here. So I like to think about if I make my number smaller, instead of 11, it's now 1.12, then we need to make my exponent bigger. So I'm essentially adding 1 here to move it to the left, just like our exponents got bigger when we moved to the left here. So if I add 1, this becomes 10 to the negative 1, and that would be the proper scientific notation for our final answer. Okay, for the second one down here, if we are dividing, we can do them in parts as well. So we can actually divide these two 4 divided by 8 is 0.5. Okay, so 0.5. So we get when we divide these numbers. And then when we're dividing two things with the same base, again, we can use our properties of exponents. We can subtract the exponents. 4 minus -6, the top minus the bottom, which would then become plus a positive, and we get 10 to the 10th. Now we're almost done, except again, I don't have a significant digit to the left, so it's not quite in proper scientific notation, so we're going to need to move this once to the right. So instead of 0.5, we're going to have 5.0, or 5, times 10 to the, and again, if I made my number bigger, we need to make my exponent smaller, right? To kind of counter adjust, or again, you can think of anytime you move it to the right, like we did here, we're getting smaller and smaller exponents, right? More of a negative number, I guess I should say up there. Okay, one last one. Here's our honors level question for properties of exponents. Solve for r. So we're going to have to utilize some stuff here. One, let's see, I see multiplication in here and a power here. We can distribute this power to both parts. So let's do that first. Power raised to a power, we multiply. R times 4 would be 4r. Okay, so we distributed the 4. We've gotten at least rid of the parentheses. And hey, I notice we're multiplying things with the same base. We can add our exponents and keep the base. And now we're going to use this idea that if I gave you like 5 to the second power equals 5 to the x power, well, I hope you know that if the bases are the same, for these two things to be equal, x is going to have to equal 2. And so we can utilize that same idea back up here. M to the something equals m to the 32. Once I've got it as just m equals m to the something equals m to the something, these somethings have to be equal. And we can utilize that idea to finish solving for r. So subtract 8 from both sides, divide by 4, and we end up getting r is 6. All right, I know I went very fast through that first part. It should be mostly review, and we will do examples in class, but make sure you have the properties down, pause, look at the expanded form, and hopefully understand why those properties exist. We'll do more examples in class. Okay, the second part of our lesson is on nth roots and rational exponents. So you guys are used to seeing this symbol. It's usually the square root, but the symbol itself has a name. It's called the radicand. Sorry. And then usually the root we're used to is the square root or the second root. So there's really like an invisible 2 here in a place called the index, or a value called the index of our root. So if you don't see that index written, like in our first example here, that usually means it's by default the second root. It's the most common root, so you don't have to write it in. Okay, so the index n basically tells us the size of the matching sets required to take anything out of our radicand. So for a square root, if I was simplifying this, right, because this is all multiplication, we can look for factor pairs. So you'd want to break this down and look for pairs. A pair of 3s means I get to take a 3 out of my radicand, and anything left over would go back inside. So the square root of 18 would simplify as 3 root 2. Hopefully we're okay with that. X to the 4th here means I have 4 x's. And again, because it's the square root, we're looking for sets of 2. So I get to take 2 x's out, which will become, of course, x squared. And there would be no x's left over. Okay, and then for y to the 3rd, we've got 3 y's. So we get to take 1 y out from that pair, but our 1 left over stays inside with 2. So simplifying this a little bit, we'd get 3x squared y times the square root of 2y. Okay, for example 2, this time we're looking at a cubed root, which is asking us what times itself 3 times would give us these values. So essentially we're looking for sets of 3 or size 3. So break 24 down, okay, into its prime factors, and we get 2, 2, 2, and 3, and we're looking for sets of 3. So I do have a set of 3 2's, which means I can take a 2 out of my radicand. And then left in my cube root, would be this single 3. My variables, x to the 4th, again, I'm looking for sets of 3, so I can make one set of 3. So we can take one x out, and our leftover x would stay inside. Y to the 3rd, we can take out exactly one set of 3y, so y comes out, and there'd be nothing left inside. So 2xy times the cubed root. Try to make sure to write that in the indent here of 3x. That way it doesn't look like y cubed accidentally. Okay, in our third example, this is the 5th root. What times itself 5 times gives me these values? Or in other words, I need sets of 5 to take anything out. So 243 is divisible by 3. That's 3 and 81. That's 9 and 9, and each of these gives us a few 3s. So 1, 2, 3, 4, 5 3s. Look at that. Exactly 5 3s. 243. It's actually 3 to the 5th power. So from that set of 5, we get to take a 3 out of our 5th root. I'm just going to leave some space in case some variables come out here. And no number left inside. Okay, if we have 6 x's though, that would be one set of 5 with one left over. Hopefully I didn't lose anybody by not drawing the visual initially. Right, if there's 6 of them, that's an x. Take out one set of 5, that's this guy, and then the one left over is in there. Okay, with y to the 5th, we can take out exactly one y, and there'd be no y's left over. 3xy times the 5th root of x. Okay, next, rational, also called fraction exponents, so rational exponents. All nth roots, so all radicals, can be written as fraction exponents. So you may not have ever seen this before. Remember, the square root of 9, this is technically like the second root of 9, can be written as 9 to the 1/2 power. Or the cubed root of 8 can be written as 8 to the 1/3 power. The cubed root of -8, which is something we haven't talked about, odd roots can actually still have a real solution when there's a negative value inside. Right? This is asking what times itself 3 times is -8. Well, in this case, there is a real answer. -2 times -2 would be +4 times another -2 would be -8. Remember, the reason that square roots couldn't have a negative number inside is because there's no number times itself twice that could equal a negative number. Well, that's true for all even roots. For 4th roots and 6th roots, things cannot have a negative value inside without creating imaginary solutions. For odd roots, though, like cubed roots and 5th roots, you'll always have a real solution. Okay, so in this case, -2 would be the value if we needed to solve here. Okay, but how can we write this as a fraction exponent? Well, in this case, we would need to show what's inside with parentheses this time, and write it as -8, the quantity to the 1/3. And that is necessary. In this case, I think whether you type it in a calculator this way or the above way, you will get the same answer, but that won't be true for different roots. So to always get the true correct answer, especially with a negative value in your radical, when you write it as a fraction exponent, use parentheses here. Okay, so in general, the nth root of x can be written as x to the 1/n. So a good way to remember this is thinking of the index of our root, or what root we're taking. Think of where you find roots, which would be kind of underground. So the root goes in the bottom here. The root goes underground. If you think of the fraction bar there, it's like your ground. Okay, so 1/n. So let's do a few examples. Write each of these in exponential form. So the 5th root of 16 can be written as 16 to the 1/5 power. 81n, so now this is more than one value. To make sure my exponent's applying to both, I'll need parentheses. 81n to the 1/4 power. Here we have, remember, this is the square root of 9. If they don't write an index, it's assumed to be the second root. The square root of 9 cubed. which is something we can evaluate, but let's just write it as an exponent. Square root of 9, so let's start with the inside here, would be 9 to the 1/2 cubed. Well, remember from our properties of exponents, when you raise a power to a power, you multiply. When you're multiplying fractions, it's the top times the top, bottom times the bottom, and we end up with 9 to the 3/2 power. Ooh, so now we have a numerator that's no longer 1. And that came from if we're raising this to a power. So let's try another example. What about if I have the square root of 9 cubed, but 9 is being cubed inside the radical? Curious. Well, let's again say that we're going to put parentheses around this value, 9 cubed. And if it's the square root of that, it's raised to the 1/2 power. Okay, so here again, I have a power being raised to a power, and we'd multiply our exponents. Top times top, bottom times bottom, we get 9 to the 3/2 again. And what we can see is actually if this value, if the whole radical is raised to a power, or if everything inside my radical is raised to a power, that ends up in the numerator of my fraction exponent. So in general, if I have the nth root of x to an m power, or even if that m is on the inside, we get x to the m over n. So the root goes in the bottom, and if we're raising it to a power that's not 1, that's what goes up top. So if we're raised to a power, that goes up top, and n, our root, goes in the bottom. Okay, so this side, this is called exponential form. And these are the two versions of radical form that are equivalent to it. So let's do a few more examples here. Write each in radical form. 5 to the 2/3. So remember the bottom is our root, so we're doing the third root of the base of 5. And we're going to raise that to the second power. Okay, now again, there's two variations for this, so you could put the square inside the radical as well, right? Kind of doing this version rather than the m on the outside. Either one is fine and correct. Okay, for our next one here, we have negative 27. We'll go inside our radicand. And the root is 3, so it's the cubed root here. And it's being raised to the 4th power. Now, if I wanted to put that 4 on the inside, we would have to put a separate set of parentheses around our negative 27 to get our equivalent value. So either one of those are correct forms. It's just using this variation or this variation. This one, though, is different than the one above, so be very careful. Here, your calculator is reading the number negative 27, take its cubed root, which ends up being negative 3, and raising it to the 4th power, which ends up giving you a value of 81. So if you plug that into a calculator, you get back 81. If you plug this into a calculator, you're going to get back negative 81. These are different. Reason being, again, your calculator would read this as the number, negative 27 to the 4/3, where it reads this as the opposite of 27 to the 4/3. So we're actually doing the exponent here first, 27 to the 4/3, and then multiplying by negative 1 in the front afterwards. It's the opposite of 27 to the 4/3. So if we were writing this in radical form, that negative sign actually goes in the front. It's the opposite of the cubed root of 27 to the 4th power, or the cubed root of, oops, the negative sign still goes in the front here, 27 to the 4th power. Okay, but that negative sign stays in front. It does not go in the radical because it was not in our parentheses here. Okay, we'll do some more examples of these in class.